Hello and welcome to Lecture 3, Part 1 of our mini course on the dynamics of circle mappings, okay? So in this first part of the lecture, I would like to discuss critical circle maps, okay? Or multi-critical circle maps. So these are homeomorphisms of the circle which have now critical points, okay? They're still invertible maps, but now they present critical points, and the presence of critical points brings several difficulties in the study of the rigidity of such maps, for example, okay? So after we see the definition and some examples of such maps, I will introduce a couple of tools. I'll talk about cross ratios and cross ratio distortion. Then I will show you the topological classification of such maps. So this is a fundamental theorem due to Jean-Christophe Foucault. Then I will discuss the geometry of such maps in more detail. So I'll talk about dynamical partitions and the real bounds. And that will be the end of part 1, okay? The material that I'll be discussing here is in detail in chapters 5 and 6 of our book. So all the missing details will be there. So first, I want to tell you what kinds of critical points we are going to be considering. So when you have a circle map with critical points, the critical points can be flat or non-flat. So here's what we mean by non-flat. So by non-flat, I mean that you have a certain coordinate system in which the map is essentially like a power law, okay? So the critical point has a certain degree, okay? Has a certain exponent, d. And the reason why we are writing f of x equal to f of c plus phi of x times the absolute value of phi of x to the d minus 1, instead of simply writing phi of x to the d power, is because you want the map to be orientation preserving always, right? So you don't want to, for instance, if d is equal to 2, if you don't write the modulus there, you just have like a turning point. And these maps that we're studying are not endomorphisms. They are homeomorphisms of the circle. They are not bona fide endomorphisms, okay? So this phi is just like a CR diffeomorphism. So essentially what this means is that up to a change of coordinates, the map looks like x goes to x to the d, or x times the modulus of x to the d minus 1 near the origin, okay? So near C, that's the way the map looks like. And so the number d, which is the degree, is also called the criticality or the type of the critical point, okay, or the order also. Okay, so this is what a non-flat critical point looks like. So you can think like, for instance, typical example, which will actually be like a generic case, would be a cubic critical point. So you have something like x goes to x to the third power, okay? In that case, you have d equals 3. And because d is odd, you don't need to write the modulus the way I wrote there, okay? Well, I should also say that in principle, it's not necessary to assume that d is an integer, okay? The theory, the study of circle maps makes perfect sense, studying maps with more generality than just maps with integral criticalities. Okay. Now, by contrast, we say that a critical point of a map, a C-infinity map, is flat if all derivatives at that critical point are 0. Okay. So typical example would be if you take the function e to the minus 1 over x squared near the origin. So that has a flat critical point there at the origin. Okay. Now, of course, flat critical points cannot happen for real analytic maps, okay? Real analytic maps are restrictions of complex analytic maps, and complex analytic maps have criticalities which are always integers, right? The degree of the critical point actually has a topological meaning here, right? Like a branch covering map. So you cannot have non-integer criticalities for real analytic maps. So what is a multi-critical circle map? So a multi-critical circle map is just an orientation-preserving homeomorphism of the circle with a certain smoothness. We assume it to be at least C3 for reasons that will become clear later. And all of its critical points have to be non-flat, okay? Now, because they are homeomorphisms, of course, multi-critical circle maps have well-defined rotation numbers. Well, it's written there that the rotation number varies strictly between 0 and 1, but that's not true. It varies from 0 to 1. It could be 0 as well. Okay, so the interval which is written as open there should be half open. Of course, the rotation number is, you can think of it as mod 1, so that's why I write it that way. So, and we will only be interested in irrational rotation numbers. We are only interested in maps which are which have no periodic points here. Okay, because I told you this in the previous lecture. When you have a homeomorphism of the circle with rational rotation number with a, you know, like a periodic orbit, you can cut the circle along this periodic orbit and reduce the study of the map to the study of a homeomorphism of an interval. And the dynamics of a homeomorphism of an interval is rather trivial, even geometrically. Okay, so and because these maps are assumed to be without periodic points, then we saw already that they are always uniquely ergodic, and so they have a unique F invariant, invariant Borel probability measure, which I call mu. So this allows us to define something that we call the signature of the map. So what is the signature? So the signature is a collection of data that characterize the map in ways that you will be clear later. So part of the data is, of course, the rotation number. The number n is the number of critical points that you have. The d sub i's that you see there, d0, d1, and so on, these are the criticalities of the various critical points. And then you have also n numbers between 0 and 1, which are defined like so. You have, for, you know, if you think of the critical points as deployed in the circle in the natural, you know, cyclic order of the circle, say counterclockwise, then you can look at the invariant measure mu and see what is the value of the measure at each one of these arcs that are determined by the critical points. So you look at two consecutive critical points on the circle, they determine an arc, and you look at the measure of this arc. So delta sub I is the measure of the arc that goes from Ci to Ci plus 1, okay? And of course, I'm looking at it cyclically, so there is a convention that C sub n is equal to C0. So this gives you a bunch of numbers. So in total, you have two n plus 2 numbers, where n is the number of critical points. But actually, only 2n plus 1 such numbers are really independent, because the sum of the deltas has to be equal to the measure of the full circle, which is 1. Okay, so the sum of the deltas is 1, so there is a relation there. But the rest of the information is really more or less arbitrary, okay? It's really arbitrary. So here's some examples. So first example is coming from a family of Blaschke products. So you can consider the following two-parameter family of analytic maps of the Riemann sphere. So these are rational maps, of course. They're quotients of polynomials, but they're special. They're what we call Blaschke products. So Blaschke products are precisely the rational maps of the Riemann sphere that preserve the unit circle, okay? They have like a general form, and this family that I'm defining here is a subfamily of that. Okay, the class of Blaschke products is much larger than what you see here. But here I'm giving you a 2-parameter family. There is this parameter omega that gives you something like a rotation. So these maps are, the maps in this family, they are this fixed map z squared times z minus y over 1 minus az, where a is real, greater than or equal to 3. But then they are post-composed with the rotation by omega on the circle, okay? And omega can be anything between 0 and 1. And a is being assumed to be real. If a were complex, in order to have a Blaschke product there, the term in between parentheses would have to be z minus a divided by 1 minus a bar z. Okay? But here, since a is real, I don't need to put the complex conjugate on top of a. Now, every map in this family, because it's a Blaschke product, it actually leaves the circle invariant, and it commutes with the geometric inversion across the circle. So it commutes with the map z goes to 1 over z bar, which is just a geometric reflection across S1. And so this is really an involution. The set of fixed points is precisely the unit circle. Okay. Okay, but now it's not difficult to see that the degree of the restriction of, if you look at the restriction of this map to the unit circle, so you have a map of the unit circle to itself, it may make sense to ask what is the degree of this map, and it turns out to be 1. Basically because this map, which is written at the top here, z minus a minus divided by 1 minus az, which is like a Möbius, it's a Möbius transformation. Because a is greater than or equal to 3, this Möbius transformation is actually switching, swapping the interior of the unit disk by the exterior. So on the circle, it has algebraic degree -1. So it's compensated by the map z goes to z squared that you see here. So 2 minus 1 is 1. So the degree of the map on the circle is 1. Okay, so this is, what does this mean? This means it's a homeomorphism. Okay? And it's an orientation-preserving homeomorphism. And it has a critical point. If A is strictly greater than 3, there's no critical point, okay? If A happens to be equal to 3, there will be a critical point precisely at z equals 1. So this is what's written here at the bottom. So it has, if A is greater than 3, then these maps f sub a omega, they have 4 critical points on the Riemann sphere. 2 of them are always 0 and infinity. It's easy to see. And the other 2 are, of course, symmetric about the circle, and they both lie on the real line, and they're given by these expressions that you can see here at the bottom. I hope you can actually see them, sorry. But anyway, there's some algebraic, there's some expression involving square roots and so on, giving you these numbers. It doesn't matter, but what matters is that if A is greater than 3, then W sub A is greater than 1, and therefore 1 over W sub A is less than 1. So these 2 guys, they are outside the unit circle. So this means that the restriction of F sub A omega to the unit circle is actually an analytic diffeomorphism when A is greater than 3, okay? However, when A is equal to 3, these 2 critical points that, were lying outside of the unit circle, one inside the unit disk, the other outside the unit disk, they coalesce at the point z equals 1, and therefore you have a cubic critical point at z equals 1, okay? So now the map f sub 3 omega for the various values of omega between 0 and 1, these are homeomorphisms. They're orientation-preserving homeomorphisms. They're real analytic, but they're no longer diffuse. They have this cubic critical point at z equals 1. So this is an example of a unicritical circle map, I should say. So it's a multi-critical circle map with just one critical point. So we call it unicritical or simply a critical circle map. Okay. The critical value is e to the 2 pi I omega, but that's less important for us right now. Okay, so these maps, f sub 3 omega, they lie at the boundary of the space of circle diffeomorphisms. Okay, so they're actually very close to these maps. There are maps with topological, positive topological entropy, but we are not going to discuss that. Another family of examples still coming from Blaschke products is the following. You can now take two complex numbers, both lying outside the unit disk, and you take an omega between 0 and 1, and you consider this Blaschke product that depends now on 3 parameters, 2 complex parameters and 1 real parameter, and it's given by this formula that you see here at the bottom, okay? And once again, z goes to z cubed has degree 3, but these two Möbius factors that you see in between parentheses here both give you a contribution of -1 to the degree. So the degree now is 3 minus 1, which is still 1. So on the unit circle, the restriction of these maps to the unit circle is still a homeomorphism, okay? And now you have two critical points. You have now two critical points on the unit circle. So these maps are bicritical circle maps. Okay, and the following result was proved by Zakeri. Said Zakeri showed that essentially every signature of the type that you see here, you know, any rotation number rho, 2 is the number of critical points. 3 and 3 indicate the degrees of these critical points, so they're both cubic, and delta can be prescribed arbitrarily between 0 and 1. What is delta? Delta is the measure of one of the arcs joining these two critical points, and 1 minus delta is the measure of the complementary arc, okay? So Zakeri proved that in this family you can realize bicritical circle maps with this type of signature. This actually raises a question which is, as far as I know, not worked out anywhere that I've seen. So it would be interesting to see, you know, if you can actually write down for every given signature a corresponding Blaschke product that, restricted to the unit circle, realizes a multi-critical circle map with those many critical points of those types specified by the signature. Now, I should say that, of course, since Blaschke products are analytic, you're only going to be able to realize special signatures having integers as the degrees, okay? Positive integers, I should say. And this kind of construction, you know, the construction of such families should be useful in the study of rigidity and renormalization, which will be topics discussed in the final 2 lectures of this course. So a third example is already familiar to us. You know, in the third lecture, I mean in the second lecture, sorry, on the second part of the lecture, I discussed the Arnold family, right? So the Arnold family it arises from this family of entire maps that you see written down there. You know, capital F sub a b of z is z plus a minus b divided by 2 pi sine of 2 pi z, okay? These are entire maps that can be quotient down to the cylinder C star, which is just C mod z. And what you get is a self-map of C star, which induces a homeomorphism of a circle. In fact, a diffeomorphism if beta is less than if b is less than 1, and a critical circle map if b is equal to 1. Okay. So we already mentioned these maps, and in fact, I even plotted the devil staircase that you get when you fix b and vary a, right? So when you set b equal to 0, of course, you only get pure rotations. You get maps of the type z goes to e to the 2 pi I a times z, okay? So A is just a rotation number in that case. But as soon as B is different from 0, what you get is no longer rotations, but the maps are still real analytic. And they are diffeomorphisms if B lies strictly between 0 and 1. Okay? Well, I mean, if B is equal to 0, you also have diffeomorphisms because you have rotations. But if B is strictly less than 1, okay, you have a real analytic circle diffeomorphism. And by varying the parameter A, you can actually cover all possible rotation numbers in this family. Now, if you set B equal to 1, then it's not difficult to see that you have a critical point. It's actually written, it's not really correct that, well, yes, it is correct. You get a critical point at Z equals 1 when you quotient the map down to the cylinder. Okay, so sorry, it is correct. Now, if you could also consider this family for B greater than 1, but then these maps, induced on the circle, they are no longer invertible. Okay. The dynamics, of course, becomes much richer because it's similar to like a unimodal map. So there is more interesting topology. There are more invariants than just a rotation number. There's like a full rotation interval. Okay. And typically these maps will have positive entropy. But we are not going to study these maps in this course. So the maps that we are studying are at the boundary between diffeomorphisms and these endomorphisms. So they are maps that lie at the boundary of chaos, as we like to say. Okay, so they are maps which lie in the transition from zero entropy to positive entropy. Okay, and this is one of the reasons why they're studied by a lot of people. Okay, so what about the topology of such maps? So now suppose you have a multi-critical circle map, and it's a homeomorphism, so you know that there are two, if there are no periodic orbits, then there are two things that can happen with the non-wandering set of these maps. They can either be the full circle, so the map is minimal, or it could be an exceptional minimal set. So the question is, can the second alternative here happen? And it turns out that it can if you allow flat critical points. So if you consider, so I mean, of course, I define multi-critical circle maps. The way I define, I kind of ruled out flat critical points. But suppose you have a circle homeomorphism, which is not a diffeo, it has a flat critical point, at least one flat critical point. What can you say about its omega limit set? Well, it could be minimal, but it also could be a Cantor set. So this was proven by Glenn Richard Hall in 1981. There exist maps of this type which are Danjois counterexamples. In other words, the omega limit set of these maps is a Cantor set. Okay. However, in the same year, Yokos proved that if you assume that you really have a bona fide multi-critical circle map, in other words, that all critical points are non-flat, then this phenomenon cannot happen and the map is actually minimal. So this is the theorem by Yokos, which I'm actually going to sketch the proof of in a while. So if you have a multi-critical circle map with a rational rotation number, then it's always topologically conjugate to the rotation with that rotation number. Okay, there exists a homeomorphism of the circle which conjugates F with the rotation by rho. Okay. Now, of course, there are equivalent ways of stating the theorem in words. So you can say just, multi-critical circle maps have no wandering intervals, because you know that if the omega limit set of the map is a Cantor set, then of course every component of the complement of this Cantor set, every open interval which is the complement, which is in the complement of this Cantor set, wanders under the map. So it's a wandering interval. Okay. So Yokos' theorem is showing that multi-critical circle maps have no wandering intervals. Of course, I'm talking always about circle maps without periodic orbits. Okay. And another way of saying this is saying what I said before, that every multi-critical circle map that has no periodic orbits is minimal. Every orbit is dense. Okay. Now, remember that in order to prove the, Danjois theorem, which states that under certain conditions, if the map is sufficiently smooth and it's a diffeomorphism and has irrational rotation number, then it doesn't have wandering intervals. We use the tools like the bounded variation, right? Like the variation of the log of the derivative of the map. Now, if you have critical points, this tool cannot be directly used, because the logarithm of the derivative of the map is clearly unbounded, right? If you have df equals 0 at some point, the logarithm is going to go to minus infinity. In fact, I'll show you a picture in a moment, a schematic picture. So in order to prove this theorem, Iocos had to introduce a kind of a new tool. I mean, it's a tool that was already present in geometry, but he was one of the first people to actually use it in dynamics, in one-dimensional dynamics, okay, which is cross-ratio distortion. I'll explain that in a little while. So here is a picture of the logarithm of the derivative of the map F, of this multi-critical circle map. In this case, there are like 3 critical points. They are denoted C sub I, C sub j, C sub k. I mean, this picture was actually, I'm using a picture that was drawn for other reasons, not for this particular reason. But you can see here that log of the f is clearly unbounded. When you're getting close to one of these critical points, the logarithm shoots down to minus infinity. Okay. So you cannot use techniques like, you cannot use something like Danjois-Coxman inequality or, bounded variation techniques like we used in the case of diffeomorphisms, like I explained in the second lecture. Okay, so what are cross ratios? Well, cross ratios, they are geometric invariants that are, widely used in conformal geometry and in one-dimensional dynamics. So these are like projective invariants, really. But in our case, we are on the circle, and we are going to look at cross ratios determined by 4 points on the circle, or more precisely for us, 2 intervals, one contained in the other. So suppose you have 2 intervals, I call them M and T, and suppose that M is contained in T compactly. So M is actually contained in the interior of T, okay? And it's a closed interval. So think of a closed interval contained in an interior of another closed interval T. And you look at the 2 components of the complement inside T. So you look at T minus M, it has 2 components, a left component and a right component. I mean, denoting these by L and R very naturally. Of course, you're on the circle, so you have to tell what is left and right, but this doesn't matter here to us. So the cross ratio is defined as this funny quotient that you see there. You take LR divided by L union M, M union R, okay, the lengths of these intervals. Okay, so the bars, as usual, the bars around the letters denote the lengths of these intervals, okay? Now, this is only one of the possible cross ratios that you can use. There are many others. For instance, you could use another cross ratio, which is just MT divided by LR. So which cross ratio you use depends on the dynamical problem that you're considering, or on the geometric problem that you're considering. And cross ratios, the basic fact about them is that they're preserved by Möbius transformations. Okay, so you can actually talk about cross ratios in the Riemann sphere for any 4-tuple of complex numbers. You can define cross ratios in terms of the numbers themselves, of the complex numbers themselves, rather than intervals, because when you're on the Riemann sphere, of course, there will be no intervals determined, okay, unless you're in special situations. But here in the circle, the cross ratio is always going to be a real number, a positive real number, which is given by this expression you see there, okay? What I'm saying is that if you're on the Riemann sphere and you have 4 points, say z1, z2, z3, z4, you can consider expressions such as z1 minus z2 times z3 minus z4 divided by z1 minus z3 times z2 minus z4, okay? So there's like a crossing, and this is why this is called a cross ratio. Anyway, the important thing is that cross ratios are preserved under Möbius transformations, okay? So they are conformal invariants. And another way of writing this formula is the following. If you take the logarithm, it's a computation. It turns out that the logarithm of the cross ratio, the way it was defined here, is minus the integral over the interval m, which is the one inside, of this rho sub t of x. What is this? This is the Poincaré density of the interval t. So if the interval t is the interval going from alpha to beta, then rho sub t is something which is defined inside t and the interior of t, and it's given by this expression that you see here at the bottom. Okay, so this is like the conformal metric on the unit disk. If you there are ways in which, I mean, if you take the unit disk, okay, and you consider the Poincaré metric on the unit disk, and you restrict it to the interval going from -1, 1, which is the diameter of the circle, what you get is a density of this type, okay? In fact, it's exactly a density like that, where, you know, beta and alpha and beta are given by -1 and 1 respectively, okay? Okay, so this is the type of cross ratios that we're going to deal with here, but I warn you that there are many other types of cross ratio that you can define. I mean, in fact, there's, I mean, give and take, you know, inversions and so on. There's like 24 different cross ratios that you can consider, okay? But they're all equivalent. Each one is some kind of a Möbius transformation of some of the others, okay? So what is cross ratio distortion? So suppose you have a continuous map, okay? And it could be any map here, any continuous map, but suppose you have some open interval, or an open set, in fact, where f is a homeomorphism, okay? So f restricted to this open set is a homeomorphism onto its image. And you consider a situation where you have two intervals, one inside the other, and both inside this open interval. We always consider M compactly contained in T. So then the cross ratio distortion is defined to be the ratio of the cross ratios. It's a ratio of cross ratios. It's the ratio of cross ratio on the image divided by the cross ratio on the domain, okay? So if you have a Möbius transformation, then it's very easy to see, I mean, it's a consequence of what I just said, that the Möbius transformations preserve cross ratios, that the ratio is always 1, of course, yeah? And cross ratio distortion is an object that satisfies a chain rule. So, in fact, the chain rule here is, you know, it's very nice, because you know, if you have a pair of intervals M and T, and you're looking at iterate Fn applied to these intervals, then the cross ratio distortion of the iterate is just the product of the cross ratio distortions of F restricted to the intermediate situations, you know, Fi of M, Fi of T, okay? So this is a nice chain rule. And there is also a very important connection between cross ratio distortion and the Schwarzen derivative, okay? So the Schwarzen derivative is this funny expression that you see here on the board, I mean, on the slide. It can also be written as, you know, you have the nonlinearity of the map. The nonlinearity of the map is the second derivative divided by the first. And another way of writing the Schwarzen is saying that the Schwarzen is equal to the derivative of the nonlinearity minus 1/2 times the nonlinearity square, okay? And when you expand this out by taking the derivative of the nonlinearity, you get this expression that you see here. So it involves the first, the second, and the third derivative of the map, right? And this is an important tool, and this is the main reason why we assume in this theory that F is at least C3, so we can actually use the Schwarzian. Now, the Schwarzian is a cocycle in the sense that it satisfies a chain rule. I'm not going to write the chain rule here because I'm not going to need it in this lecture. But if you set the Schwarzian equal to 0 and you solve, Schwarzian of F equals 0, you solve this differential equation, you realize that the solutions are precisely the Möbius transformations, okay? So the kernel of the Schwarzian is the Möbius group. So in particular, maps with 0 Schwarzian, they preserve cross ratios. So what about maps that don't have 0 Schwarzian? Well, if the Schwarzian has a sign, if it's always like positive or always negative, then there's something you can say. So in fact, maps with negative Schwarzian derivative, they weakly contract cross ratios. The cross ratio goes down when you apply the map. More precisely, this is the lemma. So suppose you have a C3 diffeo that has negative Schwarzian derivative on some open set on the unit circle, or could be also on the real line. Then for every pair of intervals m and t contained in this domain, always with m compactly contained in T, the cross ratio distortion of F on these two intervals is always strictly less than 1. Excuse me. In other words, the cross ratio of the image intervals, the image pair of intervals, is strictly less than the cross ratio in the domain. Okay? Okay. Now, I should point out that these cross ratios that I introduced are not the cross ratios that Yocos used in his original proof of his theorem. He actually used a kind of a degenerate cross ratio, which is what you get when you let m converge to t. When you have m inside t and you make m bigger and bigger and bigger until both endpoints of m touch the endpoints of t. They coincide. Okay. So in the limit, as this happens, you get a different expression of cross ratio, an infinitesimal expression. And that's the one he used. But here we are going to use this one, and we're going to show how Yocos' theorem can be proved using this this cross ratio. Okay. Now I should clarify, why, where is this Schwarzian derivative appearing? Why is it important? So the point is that when you have a multi-critical circle map, right, when you have these non-flat critical points, then near a non-flat critical point, the map naturally becomes a map with negative Schwarzian, okay? If it's C3 and it has a non-flat critical point. So suppose you have a C3 map and it has a certain non-flat critical point C. So in this proposition, notice, these maps could be, I'm not assuming here that F is a homeomorphism by any means, okay? It could be an endomorphism of a circle. But suppose you're looking at a non-flat critical point with a certain criticality, okay? And suppose that on this neighborhood, the map is a homeomorphism, okay? Then, well, first of all, you can find a neighborhood of the critical point. So I didn't tell you what W was. W was the original domain of the map, so I'm sorry. This kind of got lost. So the important point is that near this critical point, there is some neighborhood of this critical point where the map always has negative Schwarzian, okay? In fact, the Schwarzian is less than this expression, this negative expression that you see here, minus k divided by x minus c squared. So it's not difficult to see that when you have a critical point with a certain power law, if you calculate the Schwarzian derivative, it's always going to have this term, which is essentially 1 over x squared, okay? Or 1 over x minus the critical point square, okay? So the Schwarzen is always has a sign, has this negative sign. Another thing that you know is that, well, the fact that the map is a critical point which is non-flat with a certain criticality d, of course, means that you can squeeze, essentially you can squeeze the graph of f between two power laws, bona fide power laws. And so the derivative is also squeezed between two power laws, as you see there. And finally, if you're inside this neighborhood of a critical point, if the neighborhood is sufficiently small, then the cross-ratio distortion of any pair of intervals lying inside that neighborhood will be uniformly bounded. It will be bounded only in terms of the degree of the critical point. Okay? So these facts are useful. And the most useful tool in this business is the cross-ratio inequality. Okay? So Yoko's proved the cross-ratio inequality for his degenerate cross-ratio. I'm not going to state his version. I'm going to state the version for the cross-ratio that I introduced here. And this version of the cross-ratio inequality was proven by Grzegorz Świątek, a Polish mathematician. Okay? So what does the cross-ratio inequality say? It says that if you have a C3 map, which is strictly monotone, and all of its critical points are non-flat. So here you see, you allow the map to be a covering map. I'm not saying that the map has to be a homeomorphism. It could be an endomorphism of degree whatever, yeah? So suppose you have such a map. Then the following holds. There exists a constant that depends only on the map, for which if you take a family of intervals, T sub I, which has multiplicity of intersection at most m. So what does that mean? That means that every point on the circle belongs to at most m intervals of this collection. Okay. This is also sometimes we also say that the collection is m quasi-disjoint. Okay. So this family of intervals is m quasi-disjoint for some m. So every point on the circle belongs to at most m elements of this family. So suppose you have a family of intervals T sub I with this property, and inside each of these T sub i's, you take compactly contained in it, you take some intervals m sub I, okay? And suppose you look at the cross ratios of these guys, and you look at the cross ratio distortion of f on these guys. So you look at the ratio of the cross ratio of the images, f of mi, f of ti, divided by the cross ratio of mi ti. So if you look at all these cross ratio distortions and you multiply them together, then there could be zillions of these intervals. But if they are m quasi-disjoint, then you get a bound on the product, which depends only on this constant c that depends on f, and this m, which is the multiplicity. Okay, so you have this uniformity. This is an extremely useful tool. And notice that I'm not even requiring that these mi's and ti's, they are actually iterates of the same or big initial pair of intervals. I'm not saying that. I'm just taking a bunch of intervals ti. I'm taking some mi's containing them. The ti's have to be m quasi-disjoint. The map has to be C3, strictly monotone, and with non-flat critical points. Okay, and I'm not going to give you the proof, but the idea of the proof is that when you're, when your pair of intervals mi ti is kind of far away from critical points, then you can use some diffeomorphism estimate, right? That something like bounded variation or nonlinearity. You use the fact that the nonlinearity away from the critical points is bounded, and you can get a bound on the cross-ratio distortion far from the critical points. But every time you're close to the critical points, what you're going to do is, potentially things could be very bad, but you use the fact that the map near the critical point has negative Schwarzen, so it actually contracts cross-ratio. So the cross-ratio distortion in those pieces is strictly less than 1, so it does not affect this estimate. Okay? Anyway, I'm not going to go into the details, but like I said, the first version of this theorem for this degenerate cross ratio that Yocos considered was obtained by Yocos himself. And this specific version that I stated here was proven by Grzegorz Świątek. Okay, now here is a fundamental lemma about multi-critical circle maps, critical or multi-critical circle maps. So suppose you have a multi-critical circle map. So I would like to point out that now whenever I say multi-critical circle map, I'm saying it's always assumed that the map is C3, okay? And it has non-flat critical points. And suppose it has an irrational rotation number, and you look at the Q sub n's, which are the closest return times for this map F. Remember what they are from lecture 1, Pablo has told you about. The QNs are precisely the denominators of the best rational approximations to the rotation number rho. And they have this dynamical meaning that they are the closest return times for F. So if F were a rotation, then these would be really the closest approaches. You know, take a point and look at its orbit going forward. The times Qn are precisely the first return times. So each Qn is such that the rotation applied to X, Qn times, is closer to X than all the previous rotations, okay? And Qn plus 1 is defined as the next closest approach, and so on. So anyway, this is the dynamical meaning of these Q sub n's. This was explained in lecture number 1. So look at these return times, and now take a point X on the circle and look at this ratio. You look at X, you look at FQN of X, so you go forwards with the map, FQN times. Look at the distance between these 2 points on the circle. Okay, so there's an ambiguity, but after a while, there's no ambiguity because the FQN of X, as n increases, is going to accumulate on X, okay? So anyway, you look at the distance between FQN of X and divide that distance by the distance between X and F minus Qn of X. You look at the iterate going backwards, okay? So so there is the situation where you have X, you have FQN of X on one side and F minus Qn of X on the other side of X. So X is sitting in the middle between F minus Qn of X and FQN of X. And this inequality is saying that the ratio of these two intervals determined by these 3 points is bounded above and below by some constant, C greater than 1, C and C inverse, okay? So this is a nice fact which is extremely important. It's a fundamental fact about circle maps, about especially multi-critical circle maps. So this is the crucial step in the proof of Yocos' theorem. And in fact, I'm going to give you the proof of Yocos' theorem now using this lemma. So it's really straightforward. So the proof would go like this. So you want to rule out wandering intervals. So suppose by contradiction that there is a wandering interval. And you look at this wandering interval and you think of it as a maximal wandering interval, right? So it's not contained in any other, properly contained in any other wandering interval. It's really maximal. If it is maximal, this means that the endpoints A and B actually belong to the non-wandering set of the map, okay? So they are in the Cantor set. So I'm assuming that there is a wandering interval, so the non-wandering set is going to be a Cantor set. The points A and B, because J is maximal, they both belong to this non-wandering set, okay? Now, let's look at the interval determined by FQN of A and F minus Qn of A. So this is an interval on the circle that contains the point A, okay? All right. Now, because the iterates of J are pairwise disjoint, A is an endpoint of J, so FQN of A is an endpoint of FQN of J, right? So these points cannot be in J, okay? And from this, it follows that this interval delta sub n must actually contain J. Okay, fqn of A and f minus qn of A lie outside of J, and J is right next to A. A is one of its endpoints. So A has to be inside this delta sub n. Okay. However, so this immediately implies that the sequence delta sub n, the lengths of these intervals are bounded away from 0. They're always greater than or equal to the length of J, which is positive. However, because J is maximal, the point A is on the non-wandering set, so it's recurrent. So there is a sequence of return times for which fqn sub I of A approaches A, okay, as I goes to infinity. So, I mean, why is there a sequence of return times with this property? Well, there is some sequence of times going to infinity. Let's call it k sub I, such that fk sub I of A is approaching A. But then, because the qn's are going to infinity, given a ki, you can always find a q, which is larger than this ki, which has the property that fq of A, for that return time q, lies between fki of A and A, okay? So the upshot is that there is a sequence of return times such that if you look at the iterates of f for these return times calculated at A, these points are actually approaching A as I goes to infinity. But if they're approaching A as I goes to infinity, f minus qni of A has to approach A as well because of the lemma. The lemma says that the distance between fqn of A and A is comparable with the distance between A and f minus qn of A. So if the first distance is very small, the second has to be very small as well. But what does that mean? That means that the length of the interval delta sub ni is going to 0 as I goes to infinity. And that's a contradiction because we had already deduced that the lengths of these intervals had to be bounded away from 0. So no such wandering interval can be found. And so the map is actually minimal and therefore topologically conjugate to the corresponding rotation. We know that these maps are always semi-conjugate to rotations, and the only thing that we need to rule out, to establish that there is a conjugacy is to rule out wandering intervals, which is what we just did. Of course, an immediate consequence of this is, such a map is always topologically conjugate to a rotation. So if you take two such maps with the same rotation number, then of course they are topologically conjugate to one another because, they're both topologically conjugate to the same rotation. So that's a corollary, right? It's an obvious corollary of the theorem. So this now, motivates a very natural question, which is, okay, suppose you know that f and g are very smooth, as smooth as you like. Maybe they're even analytic. How regular is this conjugacy? Okay, is it just topological, or is it better than topological? Okay, remember that the corresponding problem for diffeomorphisms that we discussed in lecture number 2. The answer depended on the Diophantine nature of the rotation number and so on and so forth. Here, there's no such dependence. The results will show, the results that are known about this show that there's no dependence. In the unicritical case, in the cases where there's only one critical point, this problem has been essentially solved. But here I'm talking about multi-critical circle maps in general. So if you have a C1 diffeomorphism conjugating these two maps, then the first thing you see is that they have to have exactly the same number of critical points, and the conjugacy has to carry critical points of F to critical points of G. It has to establish a one-to-one correspondence between these two sets of critical points. So that's a necessary condition, okay, for a conjugacy to be regular, to be C1. You need this conjugacy to map critical points of one map to critical points of the other, okay? And of course, it's also easy to see that if you have the invariant measure under F, then the push forward of this measure by H is going to be the invariant measure, the unique invariant measure for G, okay? Okay, now that you know this, this implies that the signatures, the way I defined before, the signatures of these two maps have to be the same. So a necessary condition for the existence of a regular conjugacy, of a C1 conjugacy between two multi-critical circle maps is that the two maps have the same signature. Now, the conjecture, there is a conjecture, which is a rigidity conjecture, essentially says that this necessary condition is also sufficient. So in other words, if you have two multi-critical circle maps and they have the same signature, then they are C1 conjugate. They are conjugate by a C1 diffeomorphism. That's a conjecture. For an arbitrary number of critical points, this conjecture is still open. For unicritical circle maps, the conjecture has been essentially solved, okay? Except that one needs to assume a little bit more smoothness than C3. One needs C4. Pablo is going to talk about these results in his lecture, next lecture. And it also comes out of of the work that was done on this conjecture for the unicritical case, that there exists a full measure set of rotation numbers for which the conjugacy is actually better than C1. It's like C1 plus alpha for some alpha, okay? As a matter of fact, it was proven by Pablo and Wellington de Mello that earlier that if you have two C3 maps with bounded type rotation number, okay, two C3 multi-critical circle maps with the same bounded type rotation number, then there exists a C1 plus alpha conjugacy between the two maps, and alpha is actually a universal number. Okay. But the proof of this conjecture in the unicritical case is quite deep. It involves techniques coming from complex dynamics, from, in fact, renormalization of complex one-dynamical systems. So things like Sullivan's theory, McMullen's rigidity and inflexibility theory, and so on. These things are going to be touched upon in the final lecture of this course. So there's a universe behind this. So I'm not going to talk about any of these things in this lecture. Okay. All right, so let me move on to, towards what we call the real bounds, which are an essential result in this area. To do that, first I have to tell you what dynamical partitions are. So when you have a circle homeomorphism with rational rotation number, and you look at these sequence of return times, you can actually look at any point x, and you can think of the interval I sub n of x, which is a closed interval that has endpoints x and fqn of x, okay? That, of course, these 2 points determine two arcs on the circle, right? Which arc am I talking about? I'm talking about the one that contains fqn plus 2 of x, okay? Remember something that Pablo mentioned in the first lecture. He told you that the closest returns to x, to a given point x, they happen on, two successive closest returns happen on opposite sides of x. So if fqn of x is on the right of x, then fqn plus 1 is on the left of x, and so on. So I'm looking at two consecutive right returns, or same side returns. So I'm taking the interval between x and fqn of x that contains the next return on the same side, which is fqn plus 2 of x, okay? So this determines completely what the interval I sub n is. And now you consider the following collection of intervals. You look at two intervals of this type, I sub n of x and I sub n plus 1 of x, and you iterate these intervals a certain number of times. So you iterate the interval I sub n qn plus 1 times, okay? And you iterate the interval I sub n plus 1 of x qn times, okay? When you do that, you get a collection of closed intervals on the circle, and the fundamental fact here is that this collection of intervals is a partition of the circle, except for the endpoints. So these is a partition of modulo endpoints, okay? Moreover, these partitions are nested. So Pn plus 1 of x is a refinement of Pn of x, although it's not a strict refinement, but that's another story. Now, you can always look at, when you're given a partition of an interval or the circle, you can look at its mesh. The mesh is just the maximum of the lengths of the intervals in the partition. And the mesh of these partitions, of course, goes to 0 as n goes to infinity. The reason being that every orbit is dense, right? All of these orbits, the orbit of x is dense on the circle. So these partitions, they have to get, their meshes have to go to 0. They get, more finer and finer and finer. And this, again, this is a consequence of Yoko's theorem, because Yoko's theorem says that this map is topologically conjugate to a rotation. And for rotations, this happens. So this happens for the maps also. So here's an example of a dynamical partition. Of course, this is schematic only, but, I try to put in the sizes approximately what they should be, okay? So suppose you look at a map which has rotation number given by this irrational number, square root of 2 minus 1. When you expand this number in continued fractions, this becomes 1 over 2 plus 1 over 2 plus 1 over 2. So all the ANs of the continued fraction expansion of this number are equal to 2. So if you now look at the rational approximations to the rotation number, so you're starting with 1/2, then the next number is 1 over 2 plus 1 over 2, okay? And that's, the second number is 2/5. So the first number is 1/2, the first rational approximation. The second rational approximation is 2 over 5. So this, if you look at the denominators, this means that q sub 1, which is the first denominator, is equal to 2, and q sub 2 is equal to 5, okay? So if I look at the partition p sub 1 of x, I'm looking at the intervals I sub 1 of x, okay, and I sub 2 of x, which are here in this picture denoted just I sub 1 and I sub 2, and I have their images, okay? So I sub 1 is going to be iterated q2 times, so starting with 0, which is I sub 1 itself. So there should be 5 copies of it here in this picture. So you see I sub 1 at the top left. This interval is painted in green, okay? And its images are also in green. So f of I sub 1 is on the right side here, close to the bottom, okay? And then f1 is mapped to f2 here on the right, and f2 is mapped to f3 on the left, and f3 is this interval, this green interval here on the right, and finally f4 is the interval at the bottom here, the green interval on the left again, okay? So you have these intervals, and for I sub 2, you have to iterate only 2 times. So you have, the 0th iterate and the first iterate. So you have I sub 2 and f of I sub 2, okay? If you iterate once more, you're going to fall inside this interval I sub 1. So you're not going to have things which are disjoint anymore. But you see, you have these 7 intervals on the circle, and they are forming a nice partition of the circle, okay? Of course, when I drew this picture, I drew it using, as my basis the rotation with this rotation number. But, f is not a rotation in general, but the situation is going to be topologically exactly the same as this. Combinatorially, the distribution of the intervals is going to be exactly the same, okay? So this is an example of a dynamical partition. And these dynamical partitions, these successive dynamical partitions for a given map, they play an important role, a very important role in everything that we do later in this theory. So what are the real a priori bounds? The real a priori bounds theorem is a statement that is a theorem that states that these partitions, they have bounded geometry. So what does that mean? This means that if you look at every level, if you look at the partition Pn, any two consecutive atoms of this partition are comparable. So there's some constant C, okay, that depends only on the map, such that the ratio of two consecutive atoms of this partition, this ratio is bounded above and below by C and 1 over C, okay? Now, these are not, this is a statement that is not for every partition Pn of X, for any X on the circle. It's only for critical points. So if you look at a critical point and you look at the partitions Pn of this critical point, say C0, then these partitions have this bounded geometry. So this is what the real a priori bounds are saying, okay? Now, so this is intuitively, this is what it's saying. It's saying that in every dynamical partition Pn of C, for where C is a critical point, any two consecutive atoms have comparable sizes, okay? Note that rigid rotations rarely have these real a priori bounds, okay? They only have it when the rotation number happens to be of bounded type. Because when you have a rigid rotation, it's not difficult to see that the intervals I sub n, their lengths are related by this expression that you see here, this recursive expression here. I sub n is equal to a sub n plus 1 times I sub n plus 1 of x plus I sub n plus 2 of x. Okay, this is not difficult to see. And now you see that if a sub n plus 1 happens to be a very large number, then I sub n of x is going to be much larger than I sub n plus 1 of x. Okay? So, and these two intervals are consecutive intervals in the partition Pn, okay? So their ratios is going to be unbounded. So if the rotation number is not of bounded type, there's going to be a subsequence of the ANs which is going to go to infinity, and these ratios are going to become unbounded, okay? So in general, even for rigid rotations, the real bounds do not hold in general, okay? So for diffeomorphisms, which are, of course, in many cases, smoothly conjugate to rotations, they're not going to have real bounds either. So this is a phenomenon that is really, it really happens only for maps with critical points, okay? Now, I'm going to give you a statement and in a picture in the next slide, but in the picture I use an abbreviation. So I'm going to, instead of writing Fj of I sub n of C sub 0, okay, I'm just going to write I sub n upper j. The upper j means that you're iterating j times, okay? And I'm going to omit the critical point C sub 0. So given this notation, you have this picture here. So you have a critical point C0 and you have some intervals around it. The 4 intervals that you see at the top, they are part of the partition, okay? P sub n of C0. The bottom 2 are not. They are images of these intervals. So the bottom 2, the one on the right, which is labeled I sub n plus 1 qn, it's the qnth image of in plus 1, okay? So it sits inside I sub n. You know, I drew these pictures, this picture with the intervals at different levels, but they are all, of course, inside the unit circle, right? So this is just a schematic picture. So the interval I qn n plus 1, which is the one that you see at the bottom on the right, is the image of I sub n plus 1 after qn iterates. And the bottom interval that you see in the picture on the left, which is labeled I sub n qn plus 1, this is the qn plus 1 iterate of the interval I sub n. So notice that embedded in this picture is a picture of the first return map to C0, okay? On the interval, which is the union of I sub n plus 1 and I sub n. So if you take the union of these two intervals and you look at the first return map to this union, what you get is precisely a discontinuous map that has fqn on the left side and fqn plus 1 on the right side. So this is the notion already of a renormalization. So this first return map, when you rescale this to unit size, this is called the renormalization, the nth renormalization of the map F, okay? Now, the statement of the proposition is that these 6 intervals that you see in this picture, they are pairwise comparable, okay? They're comparable. So the ratio between any two of these is bounded above and below by this constant C0. There's some constant C0. This proposition is the key for the proof of the real bounds, the real priori bounds theorem that you see here, okay? Once you prove that these 6 intervals are comparable, then what you can do is just propagate this information for the rest of the atoms of the partition Pn of C0. You spread this information just using the cross ratio inequality. So here's a place where the cross ratio inequalities, it comes in as a fundamental tool, okay? I didn't tell you this, I should have told you this, but the fundamental lemma that I stated, the one that talks about comparability of symmetric intervals, is also proven using the cross ratio inequality, okay? All right. Well, so the fact that dynamically symmetric intervals, intervals of this form, f minus qn of x, x, and x f qn of x, dynamically symmetric intervals like that, they always have comparable lengths. This fact is used over and over again, okay, together with the cross ratio inequality. And it turns out that one of the crucial steps is proving the comparability of the two intervals that surround the critical point, I sub n and I sub n plus 1. To show that these two are comparable, you really have to use the critical point in an essential way. And the power law intervenes. The power law of the critical point intervenes, okay? And so this is a situation where the critical point actually helps, okay? It screws up all sorts of estimates that have to do with bounded distortion of derivatives like nonlinearity and so on, but it actually helps in this point. And it has to help because, as I told you, for diffeomorphisms, the statement is false, right? The statement of the theorem is false in general. Now, so after you know that the 6 intervals in the picture that I showed you are comparable, then you can spread this information to all other pairs of adjacent atoms in the partition using the cross ratio inequality again. So just to give you a flavor, when you look at this picture here, this figure, and you look at the 4 intervals at the top, so take 3 of them which are consecutive. Say take the first, you take the last 3 intervals. So you take I sub n plus 1, I sub n, and I sub n qn. Take these 3 intervals. They actually determine a cross ratio. The cross ratio of the interval I sub n in the middle. Okay, that's the m in the cross ratio. And the t is the union, I sub n plus 1, union I sub n, union I sub n, qn. Once you know that these intervals are all comparable, the cross ratio of these intervals is actually bounded, okay? And the cross ratio inequality is going to tell you, if you have a bunch, 3 intervals that land on these 3 intervals after a certain number of iterates, the intervals on the origin of this, they also have to have a bounded cross ratio. Otherwise, you have an unbounded cross ratio distortion, okay? That's the idea. All right, so finally, an important corollary to the real bounds theorem, the first corollary. There's going to be other consequences that I'm going to discuss in the second part of the lecture, but in this final couple of slides, or this final slide actually of the lecture, I just want to point out that you have C1 bounds. So what does that mean? That means that the return, the first return times, I mean the first return maps to the critical points, they are bounded in the C1 topology. Okay, so more precisely, what we have is the following. So if you have a multi-critical circle map, then there's some constant, and there's some level n0 that they both depend only on the map F. Okay, such that for every critical point of the map, if you look at a point, any point on I sub n of C, which is one of these return intervals, then if you iterate this point, j times, you calculate the derivative of the iterate f upper j of x, that derivative is bounded by the ratio of the intervals, the image divided by the domain. Okay, so you have this bound. So in particular, if you apply this for j equal to, if you apply this to j equal to qn plus 1, okay, then what happens is that the interval f qn of I sub n sub c of c, which is the one that goes in the numerator in this expression, that interval is comparable with I sub n because of the real bounds. So the ratio is bounded, and this means that dfqn, the derivative of fqn, okay, of x for x in I sub n, is bounded. So in other words, if you take the interval going from the critical point to fqn of the critical point, okay, and take the next return. So you take I sub n on one side, you take I sub n plus 1 on the other side. If you now take this picture and you linearly rescale this to unit size, the linear rescaling is not going to affect the derivative. So this is telling you that the renormalization, which is this rescaled return map, has bounded derivative, has uniformly bounded derivative. So this is an important fact. It's known as the C1 bounds, and informally it can be stated as this corollary, that the sequence fqn plus 1 restricted to I sub n of c is bounded in the C1 topology. And in fact, the same thing happens if you linearly rescale the map, so that I sub n of c becomes like the interval 0, 1, for example. Okay, so this is an immediate consequence of the real bounds, and I'm going to stop here. Okay, but stay tuned for the second part of this lecture. So thank you very much. Hello, and welcome to part 2 of lecture 3 in our mini course on the dynamics of circle mappings. Okay, so in the first part of this lecture, I told you about the definition and basic properties of multi-critical circle maps, and in particular, we showed Yoko's theorem, to the effect that every such multi-critical circle map without periodic orbits is always topologically conjugate to the corresponding rotation. So here we would like to examine the conjugacy, see what kinds of geometric properties a conjugacy can have. And in particular, we are aiming at establishing the smooth rigidity of such maps. So what we will do in this lecture is take an intermediate step, which is to show that these maps are quasi-symmetrically rigid, okay? So we shall present the following topics in this lecture. Well, first of all, I will define what I mean by quasi-symmetric, okay? What are quasi-symmetric homeomorphisms? And we'll give a criterion for a quasi-symmetry that involves what we call fine grids. I'll talk about quasi-symmetric conjugacies and exploit a consequence of our criterion, which is to prove Hermann's theorem to the effect that every multicritical circle map with irrational rotation number of bounded type is actually quasi-symmetrically conjugate to a rotation with the same rotation number. Okay. Then I will discuss some tools, and the most important tool is an inequality due to Yoko's involving almost parabolic maps which are near a saddle node bifurcation. Okay, and I will then state the main theorem of this lecture, which is the quasi-symmetric rigidity theorem for multicritical circle maps. I had to make some choices. Okay, so the material that I'm going to talk about here is in chapter 7 of our book. You'll find all the details there. And it, of course, uses the material from chapter 6 and 5. Okay, but there will be other interesting aspects of multicritical circle maps that we could address. And because we don't have much time or space for these things, I left out all of the ergodic aspects of this of these maps. Okay, so there are some interesting results that we present in chapters 8 and 9 of the book, some of which are actually our own results, results that were developed in collaboration with Pablo Guarino. One such result states that there are no sigma finite absolutely continuous invariant measures for these maps. This is a very recent paper. It uses a criterion due to Katz-Nelson. Earlier, a few years ago, Pablo and I proved this fact, which is kind of natural, but there was no known proof of it. So we showed that these maps actually have zero Lyapunov exponents. And recently, Trujillo proved a very nice result concerning the Hausdorff dimension of the invariant measure for these maps. These maps are uniquely ergodic, so you can look at the measure, the unique invariant Borel probability measure, which is invariant under the map, and that measure is singular with respect to Lebesgue, and you can ask for its Hausdorff dimension. Okay, so this is a very nice paper by Trujillo, but we're not going to have time to talk about any of this. But you find plenty of information in chapters 8 and 9 of our book. Okay, so let me start by addressing, what does quasi-symmetry here mean? So quasi-symmetric maps, they essentially, they're just the boundary values of quasi-conformal homeomorphisms of the unit disk or the upper half plane. Okay, so quasi-symmetric homeos for us here, the ones that will be really interesting for us are the ones which are happening on the circle. So they're homeomorphisms of the circle. So they are boundary values of quasi-conformal homeomorphisms of the disk. Okay. So what does it mean to be quasi-conformal? So geometrically, it just means that every symmetric triple of points in the domain is mapped to a triple of points in the image, which are almost symmetric. Okay, so what this means is that these 3 points, they determine two intervals, one on the left, the other on the right. So on the domain, these intervals have the same length. In the range, they have the ratio of the lengths in the range is bounded above and below by some constant. So in formal terms, here's the definition. So you say that the homeomorphism is quasi-symmetric. Well, first of all, it has to be orientation preserving. We require that. It is quasi-symmetric if it has this property that, for any point on the circle and any t greater than 0, age of x plus t minus age of x divided by age of x minus age of x minus t. So it's this ratio of the lengths of the image intervals. This ratio is bounded above and below by a constant k. Okay, so all right. So here's some properties, basic properties of quasi-symmetric homeos. So they're usually very bad from the differentiable viewpoint. Most quasi-symmetric homeomorphisms are not, they have like zero derivative almost Lebesgue almost everywhere. Okay, so they're purely singular with respect to the Lebesgue measure. But they have some regularity. They are always Holder continuous. Also, the composition of quasi-symmetric homeomorphisms is quasi-symmetric, and the inverse of a quasi-symmetric homeo is also quasi-symmetric. So they form a group under composition. However, if you try to prove these properties using, just the definition I gave you, the real variables definition, you might run into some trouble. It's not so obvious. So it's a lot easier once you know that these maps, like I said before, they are boundary values for quasi-conformal maps on the plane, because for quasi-conformal maps, you can check infinitesimally, the composition, that the composition is of quasi-conformal maps is quasi-conformal, and so it becomes a lot easier. In fact, even the condition that even the property that these maps are Holder continuous comes from a Holder continuity statement for quasi-conformal mappings as well. Okay. All right. So another important property, it's not going to be so much used in this lecture, except in kind of indirectly, but an important property is the fact that quasi-symmetric homeomorphisms are essentially the homeomorphisms that distort cross ratios by a bounded amount. Okay, so the cross ratio distortion is bounded, but this is actually not quite so. It's a little bit more involved than that. So here's a proposition that is also difficult to prove if you just stick to the real line. Whereas if you go to the Riemann sphere, if you do something like study holomorphic motions or something, you can prove this very easily. So, well, fairly easily. So the proposition states that if you have a quasi-symmetric homeomorphism, then it has a certain modulus of continuity on cross ratios. That's what this proposition is saying. So there exists some sigma, which is like a gauge, which is like a modulus of continuity, right? It's a function from positive real numbers to positive real numbers, with the property that if you look at the cross ratio of the image of two intervals, one contained in the other, then the cross ratio in the image is less than or equal to this function sigma calculated at the cross ratio in the domain. Okay, this is for all pairs of intervals m and t, where m is compactly contained in t. Okay, so I spoke about cross ratios in the first part of the lecture, so I hope you will remember what I said about cross ratios. Now, so this is not quite saying that the cross ratio distortion is bounded, because this sigma could be very weak, could be growing very, very like logarithm or something like that. So so you can't quite deduce that the distortion of cross ratios is bounded. The distortion would be the ratio, right, of the cross ratio of phi of m and phi of t divided by the cross ratio of m and t. So you can't quite deduce that the cross ratio is bounded, but you can deduce that it's weakly bounded. I mean, that the distortion of cross ratio, is weakly bounded, okay, in the following sense. If I give you, remember that these cross ratios that we're dealing with, they are always between 0 and 1, okay? So suppose you take two numbers between 0 and 1, alpha and beta, with alpha less than beta, and you look only at cross ratios, you look only at pairs of intervals whose cross ratios lie between alpha and beta. Then on that set of cross ratios, the distortion is bounded, okay? So this is what it means to have weakly bounded cross ratio distortion. And the corollary to the proposition is that every quasi-conformal, every quasi-symmetric homeomorphism of the circle has weakly bounded cross ratio distortion, okay? Okay, these facts are very useful, but what we really need for the purpose of the conjugacy theorem that we are aiming at is to give you a criterion, a kind of a dynamically useful criterion for checking that a homeomorphism is quasi-symmetric. And this is a purely geometric criterion that involves the concept of what we call fine grids. Okay, so what is a fine grid? A fine grid is just like a nested sequence of partitions of the circle. Okay, these are partitions modulo endpoints. So the intervals are, I'm thinking of intervals that are closed, and they are either totally disjoint, or when they meet at a point at one of the endpoints, a common endpoint of both of them. So the properties are the following: is that each partition in the sequence of partitions is a strict refinement of the partition that preceded it. So each Qn plus 1 is a strict refinement of the previous Qn. Moreover, when you go from one partition to the next, when you refine, each atom at a given level is broken into at most a number A of atoms at the next level. Okay, so A could be like 10. So every interval, every atom of a partition at level n is broken into at most 10 atoms at the next level. Okay. Moreover, these adjacent atoms at the same level, they are comparable. So there is some constant, I'm calling it sigma, greater than 1, such that the ratio of the lengths of two adjacent atoms at the same level is bounded above and below by sigma and sigma inverse. Okay. So these two numbers, A and sigma, they are called fine grid constants. So A is an integer, positive integer, greater than or equal to 2, actually. And sigma is some real number greater than 1. Okay, so these are the fine grid constants. All right, so I'll give an example in a moment, but first let me give you a criterion for quasi-symmetry. So this is this proposition. So suppose you have a fine grid with certain constants, and suppose you have an orientation-preserving homeo of the circle, and suppose it has the following property. If you take two adjacent atoms at a given level of one of the partitions in the fine grid, then the ratio of the lengths of the image intervals by age differs from this ratio by a bounded amount. There is some constant lambda that bounds these differences at each level. Okay, so a uniform constant. So if this happens, then it turns out you can prove that H is K quasi-symmetric, where K is something that depends only on the data that you see there, the A, the sigma, and this lambda. Okay. Although we are not going to use it in this lecture, I would like to say that there is another version of this proposition that is a criterion for smoothness. So suppose you have the same situation, but instead of having here in this equation, in display here, instead of having less than or equal to lambda, where lambda is some constant, suppose you have a constant which is actually less than 1, and instead of having, so lambda is less than 1, and suppose that instead of having lambda here, you have lambda to the n, where n is the level to which these two atoms belong. Okay? So if this happens, then actually H, you can prove that H is better than quasi-symmetric. It's actually C1 plus alpha for some alpha. Okay? That's a very useful criterion as well. All right, so now that we have this criterion, let me let me state a corollary. So to do that, let me just give you some terminology. So a fine grid isomorphism is a homeomorphism of a circle, which is orientation preserving, and maps fine grids to fine grids. Okay, it maps every fine grid on the circle to correspond to some fine grid on the circle on the target. So using this language, you can state the following corollary. So if you have such a homeomorphism, an orientation preserving homeomorphism, then the following three properties are equivalent. The first is to say that H is quasi-symmetric. The second is to say that H maps some fine grid onto some other fine grid. Okay. And the third is to say that it's a fine grid isomorphism, which means that it maps every fine grid onto another fine grid. Okay. So this is a useful characterization. So if you're trying to show that a homeomorphism is quasi-symmetric, one thing you can do is just find some fine grid that is taken by this homeomorphism onto some other fine grid. Okay? If this happens, you have quasi-symmetry. And this will be very useful later. So here's an example of a situation where it's easy to build a fine grid. So suppose you have a multi-critical circle map, and it has rotation number, which is it's an irrational number of bounded type. And let's take a critical point of this map. And let's look at the dynamical partitions associated to this critical point. Remember that I defined this in the first part of the lecture. They're defined taking the intervals I sub n and I sub n plus 1 at the critical point, looking at these two intervals which are adjacent and contain the critical point of the boundary, and you map them forward qn plus 1 times for one of them and qn for the other, and you get a partition of the circle modulo endpoints. This is the dynamical partition at level n, okay? Now, when you go from Pn to Pn plus 1, Pn plus 1 is a refinement of Pn, but it's not a strict refinement because there are some atoms, the atoms which are like the short atoms at level n, they become the long atoms at level n plus 1, okay? So you can't really, so they're not strict refinements of one another, but if you skip levels, if you go from Pn, if you go say from Pn to Pn plus 2, then Pn plus 2 is a strict refinement of Pn, okay? So let's look at the Pn's with n even. So you look at P2n, okay, and you call this Q sub n, and I claim that the sequence Q sub n is a fine grid in the case that we are considering where the rotation number is of bounded type. This is a consequence of the real bounds that I gave you on the first part of this lecture, combined with the fact that when you have bounded type, rotation number, and you have an atom at a given level, say I sub n, and you go to the next level, I sub n is broken into boundedly many intervals at the next level, okay? And each one is going to be broken at boundedly many at the next level. So if you skip 2 levels, then you're still okay. You have boundedly many. So so it's okay. I'm actually going to give you a more precise bound in a moment, but that's not really so important. And again, I'm just stating there that the reason why we skip levels, is because pk plus 1 is never a strict refinement of pk, okay? So we can then state the first theorem in this lecture. It's a nice theorem to Michel Herman, which says that if you have a multi-critical circle map without periodic points, then it is quasi-symmetrically conjugate to a rigid rotation if and only if its rotation number is of bounded type. Okay, so let's use some of the facts that we stated before to prove this theorem. Okay, so let's first assume that we have a multi-critical circle map with bounded type rotation number. No period. It's an irrational rotation number of bounded type. So this means that when you expand it in continued fractions, if you look at the continued fraction development of the number, then the partial quotients, these ANs, A0, A1, A2, and so on, they're all bounded. Okay, they're bounded by some constant A. So then the claim is that the dynamical partitions P2n of C, now I'm actually writing P sub 2n of CF to emphasize the dependency on F, because I'm going to also look at the dynamical partitions for a rotation, for the rotation with the same rotation number, okay? So the claim is that these partitions, they skipping every other level, they constitute a fine grid. And the reason was what I was stating before, is that when you go from level 2n to level 2n plus 2, each atom is broken into at least 2, okay? When you skip one level, each atom at level 2n is going to be broken into at least 2 atoms at level 2n plus 2, and into at most this number that you see here, a2n plus 1 times a2 sub 2n plus 2 plus 1 atoms at the next level, at the level 2n plus 2. And this number is bounded because the numbers a sub n, the a sub k's are supposed to be bounded. So this product is actually bounded by this bound a plus 1 squared. Okay, it doesn't matter. What matters is that it's a fixed number of atoms. I mean, it's an upper bound on the number of atoms that you can have at the next level. Okay, I mean at the next qn, right? And moreover, you know from the real bounds that these atoms, these boundedly many atoms into which a given atom at level 2n is broken at level 2n plus 2, these atoms that you have here, because they're boundedly many and because any two are adjacent, you lose a little bit on the constants, but you deduce that all of these intervals are actually comparable, okay? So they do satisfy all the hypotheses and the definition of a fine grid, okay? All right. So what does that mean? That means that so you have a fine grid, and now you look at the image under the conjugacy. So now suppose you have a homeomorphism which conjugates F to the corresponding rotation with the same rotation number, okay? Such a conjugacy exists. By the first part of the lecture, there is this theorem due to Yokos that shows that there is such a conjugacy, okay? For now, it's just topological, but now you look at the dynamical partitions, P2n, for the image of the critical point under H, and for the rotation. So there is a one-to-one correspondence between the vertices of this these partitions and the corresponding partitions for the critical circle map. And these partitions for the rotation, because the rotation is very well behaved, it's an isometry and so on, these partitions are going to be a fine grid because the rotation number is of bounded type, of course, okay? But then what we have is that H is taking a fine grid on one side to a fine grid on the other side. So by the criterion, the corollary to the criterion that I stated before, this conjugacy must be quasi-symmetric. So what about the converse? So suppose you have a conjugacy between F and the rotation, and suppose that the rotation number is not of bounded type. So this means that there exists a subsequence of the ANs that goes to infinity, right? Well, so take the critical point, any critical point of F, and you look at its image under the conjugacy. So on one side, you have the critical point. If you look at the two consecutive closest returns to the critical point, and you look at the two intervals determined by these closest returns, you know, the intervals I sub n and I sub n plus 1, for every n, these ratios are bounded above and below by some constant that is uniform, depends only on F. In particular, for this subsequence, you know, the intervals I sub n plus 1 and the I sub n plus I, they're both comparable. They have comparable lengths, okay? But for the rigid rotation, this ratio does not become bounded because, well, for the rigid rotation, you can actually show that the ratio of these lengths is slightly larger than an plus 1 when you're at the level n. So if you're at level ni, this is going to be greater than a sub n sub I plus 1, which we are assuming is going to infinity as I goes to infinity, okay? And this violates quasi-symmetry. All right. So it's easy to see that it violates quasi-symmetry because we are dealing with bounded triples of points on the domain. You can always think of this as actually anyway. You can think of these 3 points as part of a 4 tuple of points which determine a cross ratio. So you can use the cross ratio considerations that we had before, or you can actually work it out directly, okay? But this kind of situation where you have 3 points on the domain which are not exactly symmetric, but they're kind of bounded, you know, the point in the middle divides the the other two, the interval determined by the other two, into two parts which are bounded, have bounded lengths. So if you have this situation in the domain and the situation in the range is very different, one interval in the image is much smaller than the other, then this cannot be quasi-symmetric. Okay, this violates quasi-symmetry. So this proves Hermann's theorem. And Hermann's theorem has actually some interesting consequences even in complex dynamics. So if you have let's say you have a quadratic polynomial that has an irrationally indifferent fixed point at the origin. So it's a map of the form z goes to e to the 2 pi I theta times z plus z squared, where theta is irrational. Now, it turns out that if theta is a good irrational, if it's a Diophantine number, and there is a theorem of Zigo that says that you can actually linearize the map near the origin. And if you look at the maximal domain of linearization, you get a what we call a Zigo disk. Okay, and the Zigo disk is a topological disk, and it can have a horrible boundary. But Hermann showed that if the rotation number, if theta, which is the argument of the multiplier, if theta is irrational of bounded type, okay, then what happens is that this Zigo disk will actually have a nice boundary. It will have a boundary which is a quasi-circle. A quasi-circle is the image of a round circle by a quasi-conformal homeomorphism of the plane, okay, or the Riemann sphere. And moreover, the critical point of P sub theta, okay, is going to lie in the boundary of the Zigo disk, in this quasi circle, okay. Well, why is that? Because of the method of the proof, which uses a quasi-conformal surgery. The idea is that you actually start with a Blaschke product, which is pretty much the Blaschke product that I gave as the first example in the first part of his lecture. So there's this family of Blaschke products, and that has degree in the Riemann sphere. It has degree 3. Okay, it restricts to a critical circle map on the circle. And what you can do is that you can cut half of the sphere and glue in a disk, okay, a round disk with an irrational rotation with the same rotation number as your map. Okay, on the circle, you can do this gluing in a quasi-conformal map, quasi-conformal manner, and then you can invoke the so-called measurable Riemann mapping theorem and recover a new holomorphic map, which is easy to see is going to be a polynomial, or at least is going to be affinely conjugate to a polynomial, and it will be a polynomial in this family. Okay, with the argument theta being precisely this rotation number of bounded type. But all the while, the critical point was in the Blaschke product. The critical point was in the unit line, the unit circle. So this continues through the surgery, and you get that the polynomial must have a critical point at the boundary of this of the image of this circle by a quasi-conformal map, which is a quasi-circle. So this is how you prove it. That's a very, very impressionistic idea of how you prove it. Of course, there are several details here, but you use the quasi-symmetry. I mean, you use the fact that you use Hermann's theorem. You use the fact that the map on the boundary is quasi-symmetrically conjugate to a rotation, okay, to do the gluing. Anyway, so that's a nice consequence, but we are not so much interested in this. I mean, in this course, we are actually interested only in circle maps. So I'm going to state a corollary, which is kind of obvious from Hermann's theorem, but which is more relevant for our discussion here. So the corollary states that if you have any two multi-critical circle maps with the same irrational rotation number of bounded type, okay, then they are quasi-symmetrically conjugate, and moreover, any conjugacy between them is going to be quasi-symmetric. Okay. And the reason is simply because each one of them is conjugate, is quasi-symmetrically conjugate to the same rotation. Okay. Now, What's interesting here is that you don't need to assume that F and G have the same number of critical points at all. They can have very different numbers of critical points, okay? But the bounded type hypothesis is really essential. In fact, there is a recent paper that Pablo and I wrote a couple of years ago where we exploit the situation and we examine pretty much when is a conjugacy between two such maps with the same rotation number and so on, quasi-symmetric, okay? But the theorem, the main theorem in this lecture, the one that I want to talk about and at least give you an idea of the proof is something I'm calling the quasi-symmetric rigidity theorem that says that if you have any two C3 multicritical circle maps, well, the C3 here is a little bit redundant because when I gave you the definition, I assumed that multicritical circle maps were at least C3 anyway. So you have two C3 multicritical circle maps with the same irrational rotation number. And suppose they have the same number of critical points. And suppose you have a conjugacy that maps critical points of F to the critical points of G, establishes a one-to-one correspondence between the two sets of critical points. Then there is no escape. The conjugacy is quasi-symmetric, okay? When you have only one critical point, when your maps are just unicritical, this is actually, this was first proved by Yokos. So this is a generalization of a theorem due to Yokos, but there are lots of subtleties that do not appear in the unicritical case, okay? So, but you need at least one critical point for this statement to be true. You know, if you take diffeos instead and ask, you know, well, they have the same irrational rotation number, and you know they're both C3 diffeos. Can I claim that the topological conjugacy between them is quasi-symmetric? And this is false in general. In fact, there are even analytic diffeos that are topologically but not quasi-symmetrically conjugate to an irrational rotation. So I told you in lecture number 2 about Arnold's theorem and about Arnold's counterexamples. So we constructed analytic diffeomorphisms which are not C1 conjugate to the corresponding rotation, even though they are analytic. And I actually stated, I didn't prove, but I stated that Arnold actually showed that there are examples in which the conjugacy is not absolutely continuous. Okay? It's singular with respect to Lebesgue measure. Well, unfortunately, that doesn't tell you anything about being quasi-symmetric or not, because quasi-symmetric maps, as I told you in the beginning, they typically are also purely singular with respect to Lebesgue measure. So it's not going to come directly from Arnold's counterexamples, but the same method he used there to generate the counterexamples, the same criterion he used, can be used to give you, you know, using a kind of a bare category argument, you can also get counterexamples in which the conjugacy is not quasi-symmetric. Okay, but I'm not going to dwell into this. What I want to do is to give you an idea of how this theorem here is proved. And for that, so the basic idea, of course, is to apply the criterion that I stated in the beginning for quasi-symmetry. So what we need to do is to build some fine grid. And we need to build a fine grid associated with the map F in such a way that it's kind of canonical. You know, the vertices of the partitions in the fine grid, they should be dynamically defined so that, you know, if you have a fine grid for one map and you do the same construction for the other map, you also have a fine grid on the other side. And then there will be a correspondence between the two fine grids. And therefore the map, I mean, the conjugacy H will be quasi-symmetric, okay? So what I mean by canonical is what I say here is, you know, the partitions should be defined in purely combinatorial terms using just, you know, the orbits of points of maybe the critical point. You use the orbit of the critical point and use some times along the orbit which are canonically defined, okay? All right, so one first attempt would be, oh, okay, let's use the dynamical partitions, right? Maybe they, you know, taken collectively, they constitute a fine grid, but this is not going to happen unless the rotation number is of bounded type. Okay, because if the rotation number is unbounded, has unbounded type, there will be a moment, there will be many moments where the partial quotient of the continuous fraction expansion at that moment is very large. And then when you look at an atom of Pn at the level n, and you go from the level n to level n plus 1, this atom is going to be divided into more than these an plus 1 atoms, into more than an plus 1 atoms, and therefore they have to be very small, because there's a zillion of them inside the atom at level n. So this is not going to work. I mean, you cannot use the PNs directly to claim, I have a fine grid. So you need to actually, if you're going to use the PNs at all, you have to kind of group the small atoms that you see in the partitions PN. You have to group them together. But to do that, you need to understand the geometry of these guys. So what's going to happen is that when an plus 1 is very large, and you go from step n to step n plus 1 in the partitions, what you're going to see is something that, the map FQN, the return map FQN for that level, or rather FQN plus 1, is actually going to be what we call an almost parabolic map, okay? So for instance, suppose you have only one critical point, and you're considering the first return map to I sub n union I sub n plus 1. These are determined by two consecutive closest returns to the critical point, okay? So if the partial quotient A sub n plus 1 is very large, then if you look at the return map FQN plus 1 restricted to I sub n, this is the return map to the union. This map, restricted to I sub n of the critical point, is almost parabolic. You see an almost tangency with the diagonal when you draw the graph of this map, okay? So it almost has an parabolic indifferent fixed point, which corresponds to a parabolic periodic point for f. Okay, now you can look at the images. You see the picture is... I'm going to use my hands, but I mean, you have I sub n I sub n plus 1 on one side, then I sub n on the other side. I sub n is morally bigger than I sub n plus 1. So this interval here returns after qn times, and it falls exactly here on the right. And then if you apply the map fqn plus 1, it kind of goes like this. It sort of migrates like a translation, okay, from one side to the next, to the other. So these intervals, they are like fundamental domains for the dynamics of this map, of this FQN plus 1, restricted to this interval, okay? Now, when you look at these fundamental domains, there is one where you start and there's one where you end, and the one where you start and the one where you end, they're comparable to the size of the big interval containing them, okay? But the ones in the middle, if you have a gazillion of them in the middle, they can be very tiny. Now, this is a situation, this is what we, as an example of what we call an almost parabolic map. So here's the abstract definition of an almost parabolic map. So an almost parabolic map is a C3 diffeomorphism on the line or on the circle defined on a union of consecutive intervals, delta sub 1, delta sub 2, and so on. These are consecutive intervals. And your map is a diffeomorphism, okay? And it maps each delta I onto delta I plus 1, okay? All right, so, and in such a way that the following things are satisfied. So, well, first thing is what I just said. It maps delta sub k onto delta sub k plus 1, but it has negative Schwarzian derivative. It's a diffeomorphism with negative Schwarzian derivative, okay? If this happens, you say that you have an almost parabolic map. So this negative Schwarzian condition, it gives you a kind of a convexity. Sort of. Anyway. So there are two parameters here. The first is the number of intervals that you see in this chain in the domain, L intervals. So this L is called the length of the map, okay? And if you look at the ratio of the two outermost intervals, delta sub 1 and delta sub L, in the domain, if you look at these two guys, and you take the ratio of these two guys to the big interval, these ratios are given by the minimum of these two ratios is a constant sigma that we call the width of phi. Okay, so an almost parabolic map has these two numbers associated with them. One is the length, which is an integer. The other is this real number, sigma. Okay, the effect between 0 and 1. All right, so given this definition, there's this fundamental inequality due to Yoko's that states the following, that if you have an almost parabolic map of a given length, L, and a given width, sigma, then you can find a constant that depends only on the width. It doesn't depend on L, okay? With the following property, that if you look at the intervals delta sub k, so you start here, delta sub 1 on the right, say, and you come delta sub 2, delta sub 3, and so on, delta sub k. When you get to the kth interval, the kth interval has length comparable to essentially 1 over k squared. If you haven't gotten to the middle, if you are past to the middle, you have to actually count the iterates from the other side. So that's why you have this expression here at the bottom, you know, the minimum of k and L plus 1 minus k, this minimum raised to this second power in the denominator. So you think of it as saying that delta sub k, the kth interval, is essentially 1 over k squared in length compared to the length of the whole thing, okay, of the interval, which is the domain of phi. So this is a fundamental inequality. It has a nice proof. Yoko's never bothered to actually publish a proof, but the proof is really his. If you want to see this worked out, it's worked out in the book, and you know, in chapter 7. And it's also in an old paper that Wellington de Mello and I wrote, which is in JAMS in 1999. So anyway, but you know, we worked out the proof because Yoko's gave us you know, a sketch of the argument. Okay, and the idea is that you take this map and you use the fact that it has negative Schwarzian derivative to squeeze the graph of this map between two Möbius transformations. Okay, and then the estimates that you see here, they follow from corresponding estimates for the Möbius transformations. Anyway, once you have this lemma, you know, if you have an almost parabolic map, you can actually decompose the domain of the map into a way that we call a balanced way. So the way we do is easier. Instead of giving, you know, dwelling too much on the statement, let me give you a picture. Okay, the important thing here is this picture here. So at the top, you see a big interval, which is the union of all these fundamental domains. It's the domain of the map phi, okay? And then L0 and R0, you know, the one on the left and the one on the right, the big ones, they are just single atoms. They are single fundamental domains for your map, okay? So you take the one which is on the left and the one on the right. That's L0 and R0. And then they leave an interval in the middle, which is M1, okay? So now you look at M1, and on the left side, you look at two fundamental domains together. The union of them is this thing called L1 on the left, and on the right, you take two fundamental domains as well, okay, adjacent fundamental domains. So you get this interval R1, which is the union of these two guys. And in the middle, you're going to get this interval M sub 2, okay? And you keep doing this. Now, when you go from this step to the next step, you're going to define L2 as the union of 4 consecutive fundamental domains on the left, and R sub 2 is going to be the union of 4 consecutive fundamental domains on the right, okay? And you keep doing this until you cannot do anymore. You go, you know, you get powers of 2, you know, and the numbers of intervals that you get on each side are powers of 2. You have 1 and 1, 2 and 2, 4 and 4, 8 and 8, and so on, until you cannot do that, okay? And the statement is that if you do this and you use the Yoko's inequality, it's easy to see that at each level, these intervals, L0, M1, and R0, they are comparable in length. L1, M2, and R1 are comparable in length as well. L2, M3, and R2 are comparable in length, and so on. So in general, it's this statement that you see here. Sorry. You see that Li and Ri are both comparable, and they're comparable with the one in the interval that comes in the middle, which is M sub I plus 1 at each level. Okay? So this gives you a decomposition of the domain of the almost parabolic map in a balanced way. If you stop at each level, at any level that you stop, you're going to have intervals, Li, Mi plus 1, and Ri that are comparable. Okay, so this is a very useful decomposition. Okay, so to build the fine grid for F, we need, first of all, we need to first refine our dynamical partitions. So we are going to define an auxiliary partition that we denote P sub n star of C. It's going to be finer than Pn of C. So some atoms of Pn of C are going to actually be subdivided, but it's going to be coarser than Pn plus 1. So it's still not going to be, these partitions still are not going to constitute a fine grid in themselves, okay? And the idea is to look at, first at the interval I sub n of C, the one that is at level n is touching the critical point on one side, and you look at its decomposition at the next level, okay? And what you get is that there will be a bunch of intervals, and some of them are going to contain critical points for the iterate FQn plus 1. Remember that the map has several critical points. I mean, I'm thinking here of the multi-critical case, really. So you have, like, let's say 2 or more critical points. So if you look at the first return map to I sub n, it's going to pick up along the circle, it's going to pick up other critical points on the way. So when you come back, you actually have some critical points lying in some of these fundamental domains, okay? So these moments where you have critical points for FQn plus 1 for the return map, these are called critical times, and the corresponding intervals are called critical spots, okay? And there is only boundedly many critical spots at each level because the number of critical points that you have for the map is bounded, okay? It's fixed. So like I said, these intervals that contain critical points for the return map, they're called critical spots. Okay, now between 2 critical spots, you have a bridge. Between 2 critical spots, you have a bunch of intervals that don't, where the map is a diffeomorphism, where FQn plus 1 is a diffeomorphism. So these are called bridges. I'll give you a picture in a moment. So bridges, I mean, if they are non-empty, you can control their geometry and also the critical spots. So here's a picture. So in this picture, you only see, the big interval from C0 to FQn of C0. And I apologize here because I'm writing C in the text, and in the picture I wrote C sub 0. Okay, but that's okay. So you have this interval, which is I sub n of C0. And on this interval, it's acting this first return map FQn plus 1, which is kind of shifting this picture to the left a little bit, okay? Now, the intervals that you see, in the thick black lines here, these are the critical spots. Delta sub 0, I'm thinking of it as a critical spot, maybe delta sub k sub I, delta sub k sub I plus 1, and so on. Okay, so these are critical spots. And in between them, you have bridges, these G sub i's, they're bridges. And the number of bridges is bounded. The number of critical spots is also bounded at each level, okay? These bridges are called primary just because they are inside a first return interval I sub n. Then what you're going to do is you're going to use this as a decomposition of the interval I sub n. So you're going to define a new partition of the circle that's going to use these intervals, has a subdivision, And you're going to map them forward by the map F so that you actually spread these partitions, these sub-partitions to the whole circle, okay? So first there's so here's a dynamical picture of what's happening. So you have this map FQN plus 1, which is a power of F, which is a first return. And here in this picture, you see the white dots that you see on the graph, the 2 white dots that you see on the graph, they correspond to critical values. They correspond to critical points of the map. So you have 2 consecutive critical spots that are marked here, you know, delta sub k sub I and delta sub k sub I plus 1. And in between them, the map FQN is mapping each one of these guys to the next one, each one of these guys to the next one. So you have this dynamical picture here. So in between them, you have a bridge. And the geometry in the middle of the bridge is controlled by Yokosu's inequality. You see, these intervals, they're kind of decreasing in size until they get to the middle, at almost where there is almost a tangency with the diagonal. And then they start increasing again, okay? So this is the picture. And using a tool that is the cross-ratio inequality that we saw in the first part of his lecture, you can prove the following lemma. The first statement is that the critical spots, they are comparable with the interval I sub n in which they are sitting. And the bridges themselves are also comparable to the full interval. So if you look at this picture that I had given you before, if you look at these, so if you're looking at the atoms of Pn plus 1 inside I sub n, some of them are very, very tiny, like these ones here in the middle. But if you put them together into bridges and also critical spots, you get a decomposition of I sub n into boundedly many intervals, which are all comparable with I sub n, okay? And this is the key, but it's not going to give you yet, unfortunately. So this gives you an auxiliary partition. So now this partition is like this. It's, you have these atoms I sub n plus 1 and all of its images up to time qn under the map F. These atoms will remain. They stay the same. Okay, they were in Pn and they will stay in Pn star. But the long atoms, the ones that are I sub n, okay, you map them forward, but you subdivide them first into these bridges and critical spots, and then you map them forward. Okay, so you get a refined partition that I'm calling P sub n star. But these P sub n stars are still not going to form a fine grid. Okay. However, they have a nice property. They have the same property that the PNs have. They have the property that any 2 consecutive atoms, any 2 adjacent atoms of this partition, they have comparable lengths. Okay, the ratio of lengths is bounded above and below by a constant that does not depend on n. But like I said, no subsequence, not even a subsequence of these PNs will be a fine grid. So you need to do something else. So first you need to understand, well, so I gave you a lemma a while ago, a consequence of Yoko's inequality, saying that when you have an almost parabolic map, you can do a balanced decomposition of the domains of this almost parabolic map. So here what you need to do to decompose the bridges is to first of all know that these bridges really are domains of almost parabolic maps. And this turns out to be a nice lemma. It turns out that in each bridge, you know, if provided n is sufficiently large, these FQNs, which are diffeomorphisms on the bridges, they are diffeomorphisms with negative Schwarzen, okay? And therefore, they really constitute an almost parabolic map there, okay? And the constants, you know, the width and so on, it only depend on only depends on the real bounds. So if you combine that, you get this corollary that if you now map these bridges forward, you call the images also bridges. These are now secondary bridges. All of these bridges, they admit a balanced decomposition because of the lemma that I stated before for you. So now you define an auxiliary collection of intervals, which I'm going to denote a P sub n double star, okay? And again, I apologize because in some of the slides I'm writing C sub 0 and in others I'm writing C only. And you know, apologies for that. But, you know, think of the critical point as fixed. it has a fixed, just a critical point that you selected, and whether you call it C or C0 is immaterial. So I'm going to define a collection of intervals, which is not going to be a partition, it's just a collection of intervals. So the intervals there, they are all of the intervals of Pn star that are not saddle node. They are not these bridges with lots and lots of subintervals inside, okay? Together with atoms of the balanced decompositions of those intervals that are saddle node, they are these bridges, okay? So now you notice that here's a warning, right? This collection is not a partition of the circle because it contains, for instance, all of the central intervals in the decomposition, in the balanced decomposition. So when you have a bridge, you have those L's and R's, and you have those M's, and these M's are nested, and they are all inside P double star, okay? P sub n double star, okay? So this is not a partition of the circle by any means, but it's an auxiliary collection of intervals. So now the actual fine grid is going to be defined in terms of these collections of intervals and these partitions, okay? So I'll state the theorem that it gives you a recursive construction of this fine grid. So this is a proposition. I could call it a theorem because it's really the heart of the matter here. So it states that there exists a fine grid associated with the map F with the following properties. So every atom of Qn is the union of boundedly many atoms of Qn plus 1. Okay, so when you go from level Qn to Qn plus 1, you really have a bound on the number of atoms in which each atom of Qn is subdivided. And more importantly, every atom at level n is the union of atoms of Pm star for various values of m less than or equal to n. So you don't use just one level of the Pns or the Pn stars. You use various levels, okay? To form Qn, you use various levels m less than or equal to n. Okay, so each atom at level n is the union of atoms of Pm star of C for various values of m less than or equal to n, and there are three possibilities for these atoms. Either delta is a single atom of Pm star, then it's okay, you keep it, or it is a central interval of Pm double star of C. What is a central? It's one of these M's in the balanced decompositions of the bridges, okay? Or a third possibility is that delta is the union of at least two atoms of the next Pm star, Pm plus 1 star, okay, contained in a single atom of P double star of M. So this is a little bit complicated, but it's a recursive scheme. When you prove this proposition, you just do it recursively, like a little computer algorithm, okay? But the nice thing is that it is constantly using these comparability results that we have, the real bounds and so on. And in the end, you get the fine grid. And once you have this fine grid, you have the theorem, okay? The main theorem, the theorem on quasi-symmetric rigidity of these maps is an immediate consequence of this. And of course, the criterion for quasi-symmetry that I gave you in the beginning. And this is all I wanted to tell you in this lecture, okay? Like I said in the beginning, I was forced to sort of exclude the material from chapters 8 and 9, which is interesting in itself. It has all these ergodic properties of multicritical circle maps, which are not entirely obvious. But, we had to sacrifice something. And in the next two lectures, the subject will become more like, a renormalization theme. There'll be renormalization of multicritical circle maps appearing, or at least of unicritical circle maps, okay? So stay tuned for the next lecture. And thank you very much for your attention.